model at that particular time step. You're just basically interpolating erosion rates linearly here. This is between shear stresses. So it just says, oh, I got a shear stress of 2, I got a shear stress of 4. Oh, but my measured shear stress, or my actual shear stress, is 3.5. So what should be my erosion rate? And so you use this approach. Vertically, I have a depth. I'm at this location in my core profile, or my vertical profile. I have measured data that I measured up here. I have measured data that I have measured down here. But what happens in between? The decision based on all the data that has been analyzed over the years, the rate of change of your erosion rate with depth is a much faster change, and they generally, well, the decision was made to use a log scaled interpolation scheme. So your T0 here is your initial thickness. T is the actual current thickness at the depth that you're computing at that particular time. So you end up interpolating vertically according to this approach here. So now I've got erosion rate that's, so with the actual shear stress that's being applied at the actual depth, and now I'm ready to do something with it. So what do I do? Well, I need to figure out, now I have an erosion rate. What do I do? Well, if you're not simulating bed load, and you don't have to, it's optional. Even if you have non-cohesive material, you can optionally turn off the, okay, that's a very important note. The approach here kind of follows Guy approach here, which is this is fractional split here. This is the amount of material, the mass of material that's making it into suspended load versus your total erosion rate. So it's taking that erosion rate and starting to split it. Well, obviously, the fraction that doesn't go into suspended load goes into the bed load component. And again, this particular approach here only applies to non-cohesive materials. Cohesive materials, when they erode at that size class, if it's below that size class, 100% of that material just goes into suspended load. There's no splitting. But when you have non-cohesive material, you have to make this adjustment. So you're splitting here the gross erosion into the appropriate fraction in the suspended or bed load, and then it's, because this is all by size class, some of the subscripts here, the J represents the particular size class, and the S is suspended, and B is the bed load. So it kind of gives you just how we're breaking up each size class, where it goes. Got 250. We've been using, actually, I think the grain size distribution, or the probability of settling, which we'll talk about here in a minute, typically actually uses something more like 200 for Gessler's work, and then your typical split between cohesive and non-cohesive is actually more like 64, 63, somewhere in that range. I don't know why I put 250 on there. Anyways, but I can only blame myself. So let's see. So now let's talk about deposition. So now we have erosion processes. We know we have the applied shear stress. We've got material either moving out into bed load or suspended load. Now it's up in suspension. What's the next step? Well, does it deposit? And so the deposition of a particular size class of suspended material, or your grain size, you have a probability of deposition for that particular size class, your settling velocity for that particular size class times the concentration of that size class in the water column. So we have to estimate these parameters. This one we've already kind of have defined because we've either user defined it or picked one of the equations for calculating the settling velocity. This is known inside the model. So the only thing we have to actually calculate is the probability of deposition. And in the SEDZLJ model right now, Crohn's approach is used, and basically you have a critical shear stress of deposition for your material. And what this is calculating is that if your shear stress is greater than your critical shear stress of deposition in the bed, then you have 0 probability of deposition. Conversely, if it's actually that has a greater than, that's another little bug right there. That's supposed to be less than. But you have a linear relationship here between your critical shear stress of deposition here and your applied stress here. So, and I'll show you a plot here in just a minute. For non-cohesive particles, SEDZLJ uses a Gessler approach, and it uses an error function. Actually, this isn't the actual Gessler approach. This is approximation. There's a number of them, but essentially from this kind of numerical recipes document of Abramowitz and Stegen, developed this approximation approach for calculating your error function for that Gessler came up with for his probability of deposition. This is where some bugs got into SEDZLJ, and I didn't find this until I was plotting this data up so I could show you guys, and then also I'm looking at this thing and, now wait a minute, this doesn't make any sense. And ended up finding a bug that produces some really strange results, and it has now been fixed. These numbers are the correct values to use for probability of deposition of and that's now what's in EFTC 8.3 and 8.4. This is the way it's supposed to look. This is a probability of deposition plot as a function of a normalized applied shear divided by your shear stress of deposition for that particular size class. So here, if I have an applied shear stress of, well, in this, this is a ratio, so this is a dimensionless number here. So it actually doesn't matter what the shape of this curve will always be exactly the same. This one is for the non-cohesives, cohesives, and this is the shape of the Gessler curve for the cohesive or non-cohesive material. And you'll note here that when the applied shear stress is exactly equal to your critical shear stress for deposition for the non-cohesive, your probability of deposition is exactly 0.5. And then the rest of the distribution is a function of the error function. So this, if your applied shear stress is less than 0.5, essentially 100% nearly, but you're still up here at 3 times your applied shear stress, or greater than your depositional shear stress, and it's still not 0. It starts tailing out. So your probability of deposition, I don't know how far we'd have to, maybe never. It's asymptotic to your shear stress. But anyway, it's still 3 times your critical shear stress for non-cohesives. It just, you have this really long tail out there. Now, this is the function that was in EFTC up until yesterday, 2 days ago, so 3 days ago. So this is Crohn's, the same, no difference, but for your depositional probability of deposition for the non-cohesives, it's this red line. So this portion of the curve is pretty much the same, but it drops down to 0 at your critical shear stress for deposition, and then just pops back up and then starts tailing off. So anyways, just FYI, and I'm sure we'll need to have some more discussions around this to see if people agree with me, but this is kind of where we are at this point in time. Armoring. So now we've got kind of parameterized erosion. We have the parameterized deposition processes defined. Now another important process that is addressed by the SEDZLJ code and the original code with a particular option, which we're not going to talk about because it takes too much time. But let's just talk about the armoring here. So bed armoring can occur due to one of these three different processes. So you have consolidation. So your bulk density changes, so your grains are packed more densely. If you have cohesives, your charged particles are wanting to, basically they start, sticking together harder and harder. And that effectively reduces your erosion rate for the same applied shear stress. But actually that process right now, it's in the original, there's some capability in the original model to handle consolidation with time. But right now the SEDZLJ version doesn't have consolidation explicitly treated. Essentially what we're looking at though is these two options here. You have deposition of coarser material. So it either rolls along and deposits onto your active layer from upstream, and it armors that layer with coarser material. Or you have eroded out the finer materials from your finer classes that are within that layer, leaving only the coarser material. So this little diagram here kind of shows it. So you have your finer material that are essentially armored or protected from the exposed shear or your shear stress at the sediment water interface here by your coarser material. That process is controlled here through within SEDZLJ through the calculation of your active layer thickness. And as I mentioned, this is it's a computed value that changes as your applied shear stress at the sediment water interface changes. So the higher your applied shear stress, the greater your thickness. As the shear stress drops, the thickness drops. And it's based on the D50, the computed average or median grain size of your surface layer, the layer that's in contact here in your active layer that's in contact with the water column. So that's changing essentially at every time step, and as I said, it's borrowing or putting back sediment into the layers below. However, there is a term here, an active layer multiplier term, M here, which is a user-defined term that you can apply that will thicken. I wouldn't thin it. It should always be greater than 1. But you can thicken the active layer to essentially kind of capture more of the sediment below and affect more of an armoring impact on the sediment transport processes. A number typically 2 to 3 times 2 or 3 is a typical value to use for an active layer multiplier, or 1 if you. The examples that we're all running right now, I'll use 1, which just means that whatever is directly calculated is used. But to account for your armoring, this multiplier is an effective way to get more armoring processes in your system. Bed load. As mentioned, bed load can optionally be computed for any non-cohesive size classes greater than a user specified limit. Let's see, yeah. essentially what you're looking at here is movement of the material that is not actually in suspension. So this kind of is this little schematic. I forgot where I got this, but there's a lot of them out there on the web but it's kind of capturing this process of hopping. You don't see the rolling. That nice little video showed the rolling, but that's part of the processes that affect migration of material in the bed are this hopping, or another term is the saltation process, where the particles are suspended off the bed, but then they just kind of hop down because there's not enough energy in the system to keep them in suspension. But as the shear stresses increase, that same particle, there's enough, the system is energetic enough turbulence that it gets popped up into the water column and becomes suspended. But if it doesn't, it kind of gets trapped in this zone defined as the bed load thickness zone, and anything that's kind of in that region is considered bed load. And then again, we have this velocity term. So how is that done? This is the correction that we have made to the mass balance, or the transport for the bed load, is that we have added the cell area into the mass transport equation, because originally these are unit concentrations of grams per cubic centimeter, or grams per meter squared, depending upon kind of where you are internally in the EFTC code. That works perfectly fine if all your cells all have the same area, but they don't. And when they don't, you end up with a unit mass being transported from that is supposed to be representative of the entire cell area, and then gets transferred from cell to cell to cell, introducing the mass balance error when you calculate mass balance at the end. All we had to do is multiply it times area, convert it to total grams of bed load, and then we transport the total mass appropriately according to the equation down here. So your Q is your actual mass flux rate, or your area. This is actually an areal flux rate in grams per centimeter squared. And so you've got your velocity term moving it, your concentration of your bed load fluxing across that interface. Then so you're calculating all your gradients, and then you're calculating your change in bed load concentration. And this gives us zero mass balance error. So essentially the same, just kind of corrected for area. And let's see here. Few other. This T is a different, same variable ID, but it's a different definition. This is a transport parameter now, instead of in the earlier slides we were using T as the thickness of the bed. Here T is this transport parameter used here in the equation for calculating your bed load velocity. And then this applies in both you have a bed load velocity in the U and the V component associated with it. So you can calculate bed load in the X and bed load in the Y, and then your transport term. And then this term here, QB, is the exchange between the bed and the bed load layer. So that's that fraction of material that gets up into the bed load or deposits out of your bed. Yeah, and just again, we've got this, as I mentioned before, we've got the split here, so we're splitting the erosion, how much of it actually makes it into the bed layer. So then if we're assuming this CE is the equilibrium concentration in the bed load, it is not the bed load concentration, because it has the transport parameters included in it. But your CE is a theoretical equilibrium concentration balancing your erosion and deposition at the existing shear stress. So you have a um, this CE concentration here that can be computed. So if you've got CE, you've got WS, we now have, and we got CE and WS on the deposition side. You have the deposition side, the erosion. So now they're equal. Then you can calculate your probability of deposition from the bed load layer, not from the other probability of deposition that we were talking about was from the suspended load. So this is for the bed load. And so that's your equilibrium concentration in the bed, or for your bed load. And with that, all those calculations, we now have essentially a full-time step. We've handled erosion, we've handled transport, we've handled deposition, we've handled bed load. So we now essentially have fully defined those processes between the water column and the sediment bed. Any questions? Okay, moving on. That's the end of the kind of theory section. Let's talk a little bit about EFTC data structures and stuff. Just seen this, I'm sure, in the intro multiple times. There is, in your spatial variable mapping, you have this map, and we have a series of cells that are connected to one another. And they're all defined in an I along the X direction and the J along the Y direction. So if I know a cell at a particular I and a J, I know that cell number. But to speed up the computational process inside of EFTC, Hamrick years ago mapped this IJ map, and essentially it calculated a linear array of all the active cells. So it looks at a cell map. You got some rectangular cell map of IJ, and it looks at this cell and says, nope, that one's not active, not active, not active, not active. Oh, active, L+1, active, L+1, active, and then just builds up a linear array of your active cells. This is helpful for two reasons. If, number one, when you click on a cell in EE, it tells you what is your I, what is your J, and what is your L. L is not all that useful for a lot of application of the model, but if you ever get in the code and you want to look at anything and debug and, you know, delve into the source code, and, you know, any of the EE users have, you know, can get the source code if they want it, that L is quite helpful. You click on a cell, oh yeah, that's the one I want to check on in the code to see what's going on. So anyways, and K is the typical variable used to represent the vertical dimension for either in your water column or your sediment bed. Oftentimes K is used. So, and then there's some lookups. If I know my I and a J, I can calculate my or look up my L, etc., and vice versa. If I know an L, I can look up I and J. So just look at some of the control files. The files in red are the ones that are unique or specific to the SEDZLJ model. So we have bed.sdf, and this file contains kind of your global options for SEDZLJ, and also defines your critical shear stress and the properties of your active layer and your deposition layer. Your shear stresses, erosion rates, critical shear stresses, well, not shear stresses, but critical shear stresses and erosion rates, bulk densities and things. The erate.sdf is, that's where your core specific data sits. If I have 10 cores, I should have 10 sections of core definition information in the erate file. And then finally, mapping the cores that are in this file to your model domain is in this core field.sdf. And then standard restart files, but there is a hot start file capability of EFTC and SEDZLJ. So if you can run the model and the model crashes or whatever, for whatever reason you want to restart it at a, the last snapshot of your restart files, you can do that with the SEDZLJ here. And with EFTC Plus, you now have the ability with run continuation, which was not available before, but like if the model's running, it crashes, you lose power or whatever, and you've got, and you've turned on restart. That's just a little note here. If you're ever running a real project, don't ever run a model without turning on the restart file option. It doesn't cost anything computationally, and from a size perspective, it's usually negligible. Just turn on that, check that little box and say I want a snapshot every day. So that way, if something happens to the model for whatever reason, you guys lose power at the office or something, you can just restart the model, use EE. So you've got a hot start file, you've got all your output from the prior run. You turn on your run continuation, hit run. Well, you have to save, turn it on, hit save, hit run, and the model will just crank right up from the last restart file. And all your output will be in nice one continuous file. So it's a usability issue. It's quite helpful. Let's see here. Corners.imp, the rest of this, all these files are standard EFTC files. This is an EFTC Plus file. We use it a couple of different ways. Number one is we've calculated the nodal coordinate value at all the connections around a cell. So what you define up here is this is your map, your IJ, which cell's active in your IJ map. This cell or file contains your dimensions of each cell. How many meters wide and how many meters tall is it, and how deep is that particular cell, and what's the bottom elevation of that particular cell. That's defined in here. This defines, okay, where is that cell in space? So, but EFTC doesn't care what's the actual cell centroid coordinate. EFTC does not use that value anywhere unless you're simulating wind shear processes. EFTC knows that cell A is next to cell B because of the cell map. So it maps a particular I and J and maps it into a certain set of dimensions, and then it only cares about I plus 1, I minus 1, J plus 1, J plus 1, or J minus 1, etc. But obviously, first off, plotting, you need to have an actual location of the cell in the coordinate system of your model. And so we calculate this, but then we've also started using it for some of the wave calculation, Lagrangian particle tracking. Important to really have a nicely tight domain, because if you've got, the only thing that's defined in EFTC by these parameters here is a rotated rectangle. That's what you have exactly, a rotated rectangle. You don't have actually morphing of a wide cell into a narrower cell. That process is, it's not ignored because there's cell interface metrics that are computed, but that's a different issue. But with respect to what's in here and the original Lagrangian particle tracking scheme, if you can have little gaps, and we'll show you this. When you look at a map of an EFTC model in EE, there's an option to, by default, it always displays the model using the corners.imp file, which EE generates for you. This is all, you don't have to do anything. It EE generates it. But if you want to see what the model looks like really internally to EFTC, there's a checkbox. You can check it and turn off the viewing with the corners. And what it does is it displays the raw information that's in here, your rectangle and your cell rotation, all and the position, all exactly as specified in these files here, which is quite helpful for understanding kind of what's going on, especially when a model has poor orthogonality. You guys talked about that the other day, yesterday, I guess, with the intro. I mean, model orthogonality is important for EFTC. We like to try to keep that orthogonal deviation from purely orthogonal, which has a value of 0 degrees, to something under 3 degrees is fairly common, and usually that's a good target to have your model less than that. If you turn on if you look at a model and you turn off the corners and you zoom in and it's not orthogonal, purely orthogonal, you're going to start seeing spaces between the cells. And all that to say that this provides a way to to make it the presentation of your maps and things look a little bit better, but also is quite useful in trying to evaluate model behavior with when you're looking at orthogonality issues. Okay, one last file here is the time series files. This is the same file, exactly the same file, same format as used in the original sediment transport model. One file contains all your time series for all sediment classes. So you don't have to have a different file for each class. That does, historically, I think that caused a lot of trouble, if you were manually creating these files. But again, as you guys all know, EE builds all these files for you, so you don't have to really worry about it. If I have 10 sediment classes, it just appropriately builds the files accordingly. If I had 1, it builds the files accordingly. That is kind of the end of kind of this big picture overview of the code and some of the files. But we have developed a new knowledge base for EFTC. We're launching it here essentially the past week. We've started rolling this thing out. And let's see if I can go to it. Hopefully it will work. Come on, there we go. Drag it over here. This will be web searchable database with, if my internet's working, which it doesn't appear to be. Yours working? This is one reason why I'm just kind of old school that way. But when you get, does the newest distribution package have the new theory document in there? Essentially what we've done is we've taken all the different pieces of documents and papers and our work and Tetra Tech and Hamrick's work and SNL's work, and put it all into a comprehensive theory document for EFTC+. And we will be releasing that as part, finally came up, we will be releasing that as a PDF with the installation package. So it's a Word document, so you'll have it all on your machine. You can search on it and cut and paste and copy as you need to for documentation. And if there are any errors in it, I mean, it's been a massive undertaking to get this thing together. If you guys find issues with some of the equations or there's something weird going on, just let us know. I mean, we want this system to get better and better and better. So feel free to comment. But if this thing will work, here's the document we have. Basically, you know, general introduction, hydrodynamics, a general transport model, temperature and heat transfer section, sediment transport, toxics, Lagrangian particle tracking, water quality, and we have sediment diagenesis, rooted plant and epiphyte model in here, SEDZLJ's in here, original transport, it's all here. It's supposed to be all here. Everything that's in EFTC Plus should be here. Things that are not in EFTC Plus, predominantly the GBC approach for layering and the like the bed heat model. We deprecated that. We don't think that they work anywhere near as well as the Sigma Z approach that we now use, and the bed heat model isn't really needed. So those have been deprecated and they're not in this document. But if I come down here, let's just look here at the general transport equation or general transport model. Speeds, by the way, right now, I don't know how much of it's just my machine working through my phone, but it is slow, and we're trying to find ways to speed it up. I don't know why it's so. It is a big knowledge base. There's a lot in here, but it shouldn't be as slow as it is. So, you think it's an internet issue right now? Yours popped up right away? Yeah, I don't know what's doing it on mine. But anyways, this knowledge base, we really want it to just be a very robust, complete resource for EFTC Plus applications. So we are very committed to, you know, improving this, making it, you know, if there's, like as I said, there's errors, let us know. If there's gaps, let us know. You know, just we want this system to get better and better.